measurements. So you need to, the way you do gates is by teleportation through computation. And I guess they're trying to optimize minimal difficulty. So some of the, if you look at, back to that picture here, so the way you do a measurement is you open some of these gates, so you can turn on an interaction, like, so from these anyons around into these ones into this. So each of these is 2 qubits. Right now they're thinking they're only going to use one of those 2 qubits, which is a waste, but whatever. So each of these groups of 6 is 1 qubit. 1, 2, 3, 4. That's 9 qubits. These wires here are to allow better communication between the qubits. And the way you interact them is you open up loops. So like, for example, if you want to do an operation between this qubit and this qubit, you open up a loop here. And that would be like a Z tensor Z measurement, for example. And I think what this paper is saying is that certain kinds of measurements are harder than others. So for example, if you want to measure, I don't know, like that kind of loop, who knows? Or yeah, like this kind of loop, for example, to go all the way around between this qubit and that qubit, that would be noisier than this loop between these 2 qubits. And so they're just trying to figure out like how to do measurement-based computation while optimizing the length of the loops and something like that. I think they have one error rate for the length and another error rate for the number of gates you use, and who knows. And they just try to minimize the sum of the error rates, kind of. It's not complicated combinatorics. Whatever. Yeah. Yeah, okay. I don't know.
So there's like 6 switches for each qubit?
Yeah, at least. Well, there's 8 because each of these hexons, hexon because there's 6, each of these also has this little wire here. So that's not it doesn't give me another qubit, it's just for communication. Yeah, so it's 8, isn't it? Yeah. And so some of the architectures, you have more than one vertical line between them also to make communication easier.
It's like planning out a city, like the roads.
Yeah, and there's, I mean, it's harder than this even looks, because to do a measurement, you need some sort of, I don't know what all this stuff means. Is it a DAC or an analog to digital converter and these kinds of things? So, and that hardware needs to be on the same chip, and so everything takes up space, and you have to fit everything in, and you want to minimize the number of different measurements you do, because each different measurement requires a different resonator to make that measurement, and each resonator takes a large amount of space. So, I mean, it's quite a complicated engineering problem to try to do this in a scalable way, anyway. Yeah, and arguably they're doing the engineering prematurely since they don't have the basic devices set up. But who knows? Okay. So the math is really cool. So I can talk about the math of anyons, but maybe later. What else do we have here? So these are just more tables. So this table says parallelism or concurrency. How many operations can you do at the same time? The maximum number of qubits. So again, they're saying in solution NMR, so NMR of just liquids, they're saying the number of qubits you can get is maybe 10 or 20, which seems to be where it's been limited. They talk about the topology. Most of these topologies are 2-dimensional. I guess the ion traps, if you just have one trap, then maybe you naturally have like a 1-dimensional topology, but not necessarily with nearest neighbor interactions. Like on these links with where you have like 100 ions in a single trap, they're talking about you can talk to your nearest 5 qubits. So it's not, so it's like next, whatever. You different distance 5 communication, but it might not be easy to get for an ion to talk to the other side completely. Mostly they're 2-dimensional. Some are 3-dimensional. Like I guess the optical lattice ones, you can produce those in a 3-dimensional lattice, which is nice. addressability. So addressability is whether you can do different things to different qubits. In principle, like there are theories where you only need global control, so you can do the same operation on all the qubits, and you can still get interesting things done if you design it carefully, and maybe have a few places where you do something different, but most of the time you're doing everything the same on every qubit in parallel. But I think that's pretty hard to get working, and so ideally you'd really like just to be able to address every qubit whenever you want. Okay, operations on all qubits. I don't know. I mean, there's probably there could well be a gap between what we think and what they think. What I mean is, between the theorists and the experimentalists, right? We have this nice model of quantum circuits, qubits talking to their neighbors. Like basically, the way we think is we think we have quantum circuits. Maybe there's some limited geometric locality, so you can't do a CNOT gate from this guy to that guy, but that's not so hard to worry about. And then the other thing we think about is, okay, there's going to be some noise on every gate, but we say the noise on this controlled NOT gate is going to be independent of the noise on this controlled NOT gate, which might not be true in practice. So maybe our theoretical models aren't exactly right in practice, but on the other hand, it could be that there's more interesting things that the devices use, that the devices open up for us that we're not using because the experimentalists aren't theorists, and they don't know all the possibilities. And so so I think a few examples of this would be like maybe you could say just the concept of qubits. I mean, maybe some device